Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello students, welcome back. I'm Atkwate Alan, who will be taking you through chemistry, senior 6. I hope you're safe and ready to take on this lesson. We are still on ionic equilibrium, unit 9, which is the pH of acidic and alkaline solutions, and lesson 5, that is for today, which is salt hydrolysis and the pH of solution. So basically at the end of this lesson, I expect every student attending to be able to, 1, classify different salts depending on the pH of their solutions, either acidic, basic, or neutral. 2, illustrate with equations the cation and anion hydrolysis. And 3, to predict whether a specific salt will undergo hydrolysis or not. So those are the 3 objectives we are to work on. But before we go to today's lesson, I want us to first take a recap or a review of what we looked at in the previous lesson. We were looking at the pH of acids and bases. So we did a few calculations, then we ended up having the pH scale and what it implies. As you can see directly, from the pH of 1 to 6, that is, we have the acidic solutions, of course, with varying strength, whether it is strongly acidic or weakly acidic. Then from pH of 8 up to 14, we have it as basic, and that is where we have weakly acidic, weakly alkaline, and strongly alkaline. Then we looked at the effect of the strongly alkaline and strongly acidic solutions can do onto the body, as an example given on the illustration. We ended by having the exercise 4, which is a table to be completed. So I want us to quickly review it based on the calculations you did and the answers, and so as we can come up with the answers which are correct according to the concentrations we are having. Something you need to recall about is when we're looking at the pH of acidic and basic solutions, we can't eliminate the use of Kw, which is the equilibrium constant for water at standard conditions. In this case, they are 25 degrees Celsius, since Kw changes as temperature changes. So that is an expression you have to be recalling about, and how we can get the pH and how we can get the pOH. We covered them in detail. So let's look at the table. What was it expected of you? We're having the concentration of hydrogen ions or hydronium ions, indicating we can substitute in this formula to get the concentration of OH ions. And if we have the concentration of OH ions, we can get the pOH and the pH, since we have the hydronium concentration. Then from these 2 hydronium ions and the OH, we can determine whether the solution will be basic, neutral, or acidic, based on the concentrations. So I hope you did calculate. Let's look at what were the expected answers or the solutions. So the black ink or the black color is the value that was initially given to us. Then the blue is the answer for OH ions, and red is the answer for hydronium ions. So this is the whole table completed. Check through with what you had already filled in and make corrections. So how do we come up with the answer to whether it is basic, neutral, or acidic? You look at the concentration of hydronium ions relative to the concentration of OH ions. Which one is in bigger amounts? If the hydronium ions is bigger, then it will neutralize the OH ions, making the solution to have a net hydrogen ions, which gives it acidic nature. And that is the answer here. The concentration here is bigger than this, making the solution to be acidic, and that is the reason. The reason is based on the concentration of hydronium ions and OH ions. Compare your answers with this, and that makes it up. In terms of the review for that part, let's go to our today's part, which is salt hydrolysis. Well, I'm pretty sure when one talks of salt, the first thing that comes into your mind is this common salt, sodium chloride, that we eat, or sometimes called table salt. Yes, it is a salt, but we have a wide range of salts appearing or coming in different structures, different colors, and so on. Let's take a look at the slide. Calcium carbonate is actually powder, white in color, but we have like copper sulfate, which is a big crystal. It crystallizes to form big particles. It is blue in color. We have green, like copper 2 chloride. We have some crystalline components, small crystals, like zinc chloride. So when we talk of salt, we're meaning all these categories of salts as you can see them. Different colors, different structures, and of course, different properties. So you see senior 3 and the lower sections, and even senior 4, you talked about salts and how they are prepared. We shall not go deeper into that. Our aim is on salt hydrolysis. But we shall be borrowing that knowledge as we look into the salt hydrolysis. So, salt hydrolysis. Of course, as I told you, we can't talk about salt hydrolysis without looking at neutralization. So mostly salts are formed or using different methods. I will only stick to one, which is neutralization, because it goes hand in hand with hydrolysis. How are the two related? When you have a base reacting with a salt, with an acid, which we call neutralization reaction, they give salt and water. Get that salt, react it with water, you will get the acid and the base that were initially making it up. And that is what we call hydrolysis. Ideal hydrolysis is a reaction of the cation or anion of salt with water. We shall go deeper into details to look at the cation and look at the anion of the salt. So, a point to note in here is when the hydrolysis reaction occurs, there is a change in pH of the solution. Sometimes it becomes basic, indicating it has the pH greater than 7, or it becomes acidic, indicating it has the pH less than 7. But in either case, or sometimes it remains neutral. So when you have a salt undergoing hydrolysis, there is a possible change in the pH. That's why we are bringing in salt hydrolysis and the pH. And of course, what brings that pH change is because of the OH and the hydronium ions set free in solution. We're going to take a deep study on the 4 salts that we're having. 4 salts. Potassium carbonate, ammonium chloride, sodium carbonate, and aluminium chloride. But you notice 3 have been clamped together, then aluminum chloride set aside. Let me explain what is happening in here. Again, using our pH scale chart with the different colors, 7 neutral with the light green or the green color, then pink, red, and yellow onto the acidic side, then light blue to deep blue onto the basic. So these beakers are having distilled water with the universal indicator. As you can notice, the color is uniform. It's similar or the same, and that is green color, indicating they are at neutral. We do not have either of these solutions being acidic or alkaline. So what we're going to do next is to add the salts of their respective salts. In other words, we're going to add potassium carbonate in this beaker, ammonium chloride in this beaker, then sodium hydrogen carbonate in this beaker, and aluminum chloride in this beaker, and see what happens. So here are the results of the addition. Take a close look. Compare these beakers with our pH scale. What do you notice? I pose a question. What do you notice? Let's start with potassium carbonate. What color is potassium carbonate? Look closely on our pH scale. Potassium carbonate, it ranges within 10 to 12. It's within this dark blue color, indicating it is possibly strongly basic or strongly alkaline. Look at ammonium chloride. It has almost the pH of 5. The color is 5. The color is yellow with the pH of 5. And look at sodium hydrogen carbonate. It's around light blue, 8 or 9 in pH. And finally, aluminum chloride, around 4 or 3. It is much red than the yellow color of ammonium chloride. So what conclusions can we make from these solutions? Potassium carbonate and sodium hydrogen carbonate are basic, but of course the strength differs. Ammonium chloride and aluminum chloride are acidic, but again, the strength differs. So, what brings such a difference in pH for different solutions? The answer goes to the point hydrolysis. But let's quickly look at the classes that we mentioned above in respect to how they are formed and what happens. So, when an acid and a base react together under neutralization, 3 cases are possible to result. Either a neutral salt. Neutral salt comes when you have a strong base reacting with a strong acid. An example is the sodium chloride, which comes from sodium hydroxide and hydrochloric acid. So, like as most of us know, it is neutral. We shall see exactly what happens later on. Then we also have acidic salts. These come from a weak base and a strong acid. An example here is ammonium chloride. As we noticed, it is acidic because it comes from a weak base, ammonium hydroxide, and a strong acid, HCl. So its pH is less than 7. Talk about basic salts. You have a strong base, sodium hydroxide, for instance, or potassium hydroxide, and a weak acid, maybe ethanoic acid or any other organic acid. to form sodium ethanoate. But from our example here, we're looking at potassium carbonate, indicating we had potassium hydroxide and maybe weak carbonic acid. So those are the three classes of salts we are to look in. Let's look at exactly what happens when hydrolysis occurs. What brings those different pH values, or what brings the change in the color in presence of universal indicator? Let's start with the neutral salt, for instance. This is sodium chloride. For it does not undergo hydrolysis. It is the usual salt that we take. When you dissolve it in water, it simply dissolves. Let's look at acidic salt. We looked at ammonium chloride. So what happens is when you dissolve ammonium chloride, it undergoes what we call cation hydrolysis. Cation hydrolysis is the reaction of the cation from a weak base with water. This is ammonium chloride. It has the ammonium ion. This is the cation of the weak base, ammonium hydroxide. So when this salt is added in water, this cation loses a proton, or it acts as an acid, donating a proton to water molecule to form hydrozonium ions. The presence of these hydrozonium ions make the solution to be acidic. Of course, as we looked at the strength of the weak acids, this is acting as a weak acid. Depending on how much of the hydrozonium ion is set free, then it can have the color indicated. So for the basic salts, example, the potassium carbonate, the sodium hydrogen carbonate, and the sodium ethanoate, when they are dissolved in water, the ethanoate ions in this case acts as a base, taking a proton from water to form an ionized ethanoic acid and OH. So it releases OH in solution, making the solution to be alkaline. All these, as we notice the example like potassium carbonate or sodium hydrogen carbonate, they release OH in solution to be alkaline. So I want us to look on the sodium chloride, which is neutral. This is exactly what happens. Remember, it comes from a strong acid and a strong base. So we have the ions, for instance, sodium ions from the strong base, sodium hydroxide, and the chloride ions from a strong acid, hydrochloric acid. So as a salt, when you dissolve it in water, the ions are simply dissociated. It is not hydrolyzed, but simply dissociated. The sodium ions are surrounded by the partial negative part of oxygen. Then the chloride are surrounded by the partial positive of hydrogen in water. This is what we call dissociation. They are separated from each other. This is a crystal, so they are dissociated. They are not hydrolyzed. That's a point you really need to master. So that is the three cases we can look at, but I have a special case, and that is for aluminum chloride. Aluminum chloride is a special case. Yes, it is acidic salt, but how it comes about and what exactly takes place in the solution differs from the other two cases we looked at, for ammonium chloride, for instance, and the potassium carbonate. This is the example of the ammonium chloride we looked at. So let's look at aluminum chloride. It is a case, it falls in the salts of transition metal ions or strong metal ions. Look at example, iron 3 chloride, aluminum 3 chloride, the nickel 2 ions, the chromium 3 ions, all those are the transition metal ions. They have a unique character. Because they are small and highly charged, For them, when they are in water, they tend to attract water molecules. Due to the high charge density and due to high charge density, they attract water molecules to themselves. The end reason is they polarize the OH bond. Look closely at the last part. They polarize the OH bond by pulling strongly the electrons on oxygen to the highly charged cation. So this OH bond is made weaker. In the presence of water, the water molecule will donate electrons on the hydrogen positive, forming hydronium ions. All this bond will be broken and set free in a solution, bringing the strongly acidic solution of aluminum chloride. So it is a unique character for the salts of strong metal ions in the transition metals. That's why I will take you a little bit back. That's why I separated it to be different from these three. For it, it reacts or it interacts with water differently. So let's make a summary. What do we conclude from what we looked at? Simple. Strong acid and a strong base, under neutralization, they yield a strong salt, which is neutral. It does not undergo hydrolysis, indicating its pH remains 7. A strong acid and a weak base, they result in a salt which undergoes cation hydrolysis. Example, ammonium chloride. The cation ammonium ion hydrolyzes in water, producing acidic solution, pH less than 7. A weak acid, a strong base, example, ethanoic acid and sodium hydroxide, they result into sodium ethanoate, which is a strong salt. But when it is hydrolyzed in water, it forms a basic solution because of the anion, the ethanoate ions, which interact with water to produce a solution with pH greater than 7. Now, a puzzle in here. What happens if you have a weak acid and a weak base? What happens if you have a weak acid and a weak base? Ammonium hydroxide and ethanoic acid. Yes, they react, forming a salt under neutralization, but the hydrolysis of this salt depends on Ka and Kb. That's why we said it depends. So how is that coming about? You understand from our previous lessons, Ka ionization constant for a weak acid, Kb ionization constant for a weak base. Because in here we are involving the cation acting as a weak acid and the anion acting as a weak base, so they undergo ionization in water. The end result is whichever is stronger, whichever is in higher amounts, whichever is in higher concentration, then wins, and so making the solution either basic or acidic or sometimes neutral. For instance, ammonium ethanoate has a neutral solution because the Kb from ethanoate ions is equal in magnitude to the Ka of ammonium ion. The Kb and Ka are equal in magnitude, so we do not, in simple, they are equally ionizing in this case. The amount of OH is equal to the amount of hydrozonium ions set free, making the solution neutral. But when you look at ammonium fluoride, it is different. For it, it is basic because of the fluoride ion, which is relatively bigger, so it has a higher polarizing effect. It reacts with water to produce OH, which is in a higher amount than hydrozonium brought in by ammonium. So here the difference is on the anion, making the solution to be basic. That's why we said it depends on the cation and anion hydrolysis. Which one is stronger than the other? So that is a point you really can't miss out. Ensure that you take note on that. So as I conclude, I'm leaving you with the activity. Basing on what we looked at and what we concluded at, what do you really look at in this activity? The activity asks you to write the ionic equation of what happens when you dissolve potassium carbonate in water and what will happen to its pH. Make sure you look closely and refer to what we looked at, then you can come up with the equations. These are the solutions we looked at, so I want you to formulate their solutions. Then predict with a reason whether these following solutions would be acidic or basic. And that is the activity. Make sure you go through it. Thank you for your attention during the lesson. I hope you picked something. Please stay safe. Follow the Ministry of Health regulations. I want to see you next time. Nice time.